Okay, well, welcome to the second hottest of 2019. We will, as usual, have a 60-minute talk, and then we will have some open discussion afterwards for about 30 minutes. And the routine is just like usual. If you have any questions, you just unmute your microphone and interrupt the speaker and ask your questions. And we want to encourage people to do that as much as possible. When you're not asking a question, it helps to keep your microphones muted because it causes echo otherwise. And I may sometimes mute your microphone if you forget to unmute it. So just be aware of that. It's also great if you can turn on your video. It just helps make it seem like like we're in the same room, more like a regular talk. So we appreciate it if you can do that. We will be recording the talk, and then afterwards we will check if the speaker agrees for us to post it. We have a hottest YouTube channel where it will appear if it's posted. And I guess that's all the preliminaries. That was just the usual spiel. So then today we're very happy to have Nima Rasekh from the Max Planck Institute in Bonn. And the title of his talk is Algebraic Topology in an Elementary Higher Topos. Take it away, Nima.
Okay, well, first of all, I want to thank the organizers for giving me the opportunity to speak. And thank you all for, not being right here, but being here online. So before I start my talk, I wanted to kind of point out that, obviously the seminar is called Hottest, so it has a hot in it. So it's homotopy type theory, but I'm not actually a homotopy type theorist. So my area of research is mostly high category theory, or probably exclusively high category theory. And some of my work kind of has connections to homotopy type theory, and the goal of it is to talk about that today. So in particular, this means that if people in the audience might not all be familiar with high category theoretical concepts, so in case you have any questions, and in case something is unfamiliar and then you're not following, then feel free to ask. I have tried to include some basic ideas that I will need, but I try to keep it at a minimum. And if you have questions, then feel free to ask. Okay, so the title of the talk is Algebraic Topology in an Elementary Higher Topos. So let me say something about this word elementary higher topos first. So going by how you can find points on a map, I will start by triangulating the word elementary higher topos, i.e. finding three corners, and somehow this word should be in the middle of those three. So an elementary higher topos should intuitively be in infinity one category that kind of sits in between these three concepts. So it should behave like the infinity one category of spaces, which I guess is the most famous infinity category out there. On the other hand, it should be a model for homotopy type theory. And finally, it should generalize an elementary topos, which is a kind of one category, which itself is related to the category of sets, and also on the other hand to sheaves of sets. So it tries to interpolate between three different concepts. Let me say a little bit more about number two, given that this is a hot audience. So let me say a little bit more about how the relation to hot is. So in an ideal world, we should have two things. One, an elementary higher topos should be a model for homotopy type theory. So that, for example, would be very useful. If that was actually proven, then that would mean if I want to realize whether something is independent of hot, I could try to find two elementary high toposes, one which satisfies certain thing and one which that doesn't hold, for example. There's also kind of a little bit of a reverse argument for that. So homotopy type theory should be the internal language of an elementary high topos. So if I want to reason internal to an elementary high topos, I should use homotopy type theory. However, so to be very clear, we don't actually have that precise result yet, right? So there's some results in this area, but there's no actual result that exactly states these two results yet. And a lot of the problems is exactly that type theory has a kind of strictness to it, whereas infinity one categories are kind of by nature very, very kind of flexible, and it's sometimes very difficult to interpolate between those. But that is kind of to this, while it's not an actual theorem, it is kind of what guides our thinking. So if I want to think about elementary higher topos, very often I try to compare the results with results in the world of hot. And that is exactly what this talk will be about.
When you say strictness of type theory, are you talking about the associativity of composition or substitution?
I'm talking about more general. So I think normally we model type theories via things like contextual categories or via other models. And normally they have like more strict definitions of everything. Yeah. Whereas in Infinity One category, everything is like all these notions are defined up to weak equivalences.
Because in type theory, we want the substitutions to be associative. Doesn't matter which order we bracket it. And as a result, it needs to be an equality rather than an isomorphism.
I mean, I'm not a type theorist, so I will not comment. My understanding is that, yeah, something along these lines. I'm sure that type theorists will have like a better understanding, but like, so my knowledge is like where the category theory of type theory starts. I know that normally we model type theories via like certain categories. So like I said, like contextual categories. And then the goal is to translate those into certain Infinity One categories. So there is work of Kapulkin, for example, who does that and who builds like locally Cartesian closed infinity categories out of them. And even there, it turns out it's like really tricky to kind of go through these steps and do that.
Sorry, I'll just say that you're both right in a sense that there is a stratification from infinity categories to one categories, and then there's a stratification from one categories to models of type theory, which would be even stricter than one category because pullbacks would be chosen up to equality. So both of these things have issues that need to be solved.
Yeah, so the expectation is that presumably that will work. And so it is what guides our thinking, but it's not an actual theorem written down in a book or something yet, at least. Okay, so I'm say a little bit about what I mean. There's just like a little bit of Infinity One category theory. So when I think of Infinity One category, like whatever it is, it should have a notion of objects. And for any two objects, I should be able to associate a mapping space, which I personally think of as a count complex, but if you think of topological spaces, that's also fine. And so the mapping spaces have a notion of composition, but that composition only works up to homotopy, which whatever that means. The important thing right now, like one of the important things I will use is that whenever we have a mapping space, we can talk about homotopic maps. So I can take two morphisms and ask whether they are homotopic, meaning that the two morphisms are connected by a path inside the mapping space. And accordingly, I can also generalize the notion of an isomorphism to an equivalence. So an isomorphism classically is a map that has an inverse, i.e. another map that composes to the identity. An equivalence is a map that composes to a map that is equivalent to the identity. So in particular, every isomorphism is an equivalence, but the opposite is not necessarily true. And the important upshot is that everything that we are familiar with in the world of one category theory, limits, colimits, adjunctions, presentability, all these kind of concepts do generalize to the infinity categorical setting in various forms. There's one concept from Infinity One category theory I would use more often, and so I will actually give a definition here. And that is the core of an Infinity One category. So the core is by definition the subcategory that has only the equivalences. So I just defined what an equivalence is, and I'm saying if I take the subcategory of an Infinity One category, which I throw out all the non-invertible errors, all the non-equivalent errors, then what I'm left with is I call it core. And the core is by definition an Infinity One groupoid because, well, everything is invertible. But Infinity One groupoid, so that's an Infinity Zero category, so it's a space. It has the data exactly of the space. And how do we think of it as a space? An object in the core is exactly the point. The morphisms are not the paths. And here I'm using the fact that, well, every morphism is invertible and paths are also always invertible. So there's kind of like a correspondence between them. And so the higher cells then give us the higher homotopies of those paths, of those morphisms. Yeah, let's give a couple examples. So spaces themselves form an Infinity One category, right? So I can always define a mapping space. I will just denote it by spaces with a curly S. We also have, if you fix a cardinal, we can also like restrict spaces and talk about spaces of a size smaller than kappa, so kappa small spaces. And notice, so there's like a fun fact, if I take kappa small spaces and then take the core of that, I get a space. But that space is not kappa small. So this is kind of like the homotopical version of like Russell's paradox, right? We cannot have the space of all spaces. And that will come up later in the talk. Another example is, well, you have the infinity one category of infinity one categories. And again, the same principle applies. So it's not an object of itself. And following like convention, every standard one category is in particular infinity one category, using the principle basically that everything that's enriched over sets is also enriched over spaces. Okay, so that's all I'm going to say about infinity one category theory. So if there are any questions up to here, then right, then I move on. So my goal is now to define what an elementary higher topos is. I haven't actually told you. So the first definition I need is that of the subfunctor. So if C, and C will always be in infinity one category. If C is finite limits, then I can define this functor from C up to set. What does it do? It takes an object C to, well, equivalence classes of monomorphisms, which is a set. I should point out here that monomorphism here is in the infinity one categorical setting and not maybe the set theoretical setting. So, for example, a mono of spaces is not an injection. A mono of spaces is an inclusion of path components. So there are two ways to phrase this. I can phrase it as like saying that this map, the diagonal map is basically equivalence. But even more conventional, I can just like say that the map is an inclusion of path components. So if I restrict to any path component, it's an equivalence. Now that I have the subfunctor, I can ask whether it's representable because it's valued in set, so I can ask for representability. And whenever this functor sub is representable, we call the representing object omega a subobject classifier. And the naming is very appropriate, right? It's classifying subobjects. In spaces, the subobject classifier is exactly the two-element set. So 0, 1. And the way I can find a subobject is by just mapping any path component that is in the subobject to 1 and any path component that's not in the subobject to 0. Well, and then I can exactly recover any subobject by pulling back along the universal, like the map from 1 to the object 1, to the element 1. Okay, so now we need one more thing to be able to define elementary topos. So we only need to generalize the subobject classifier. So this part is a little bit more notation heavy. So first we have this functor, which we just C over something, well, which takes an object C and gives me the over category. Well, I haven't defined the over category, but it's just the category which has objects maps with codomain C. And so I can, this itself is obviously an infinity one category. And if I have finite limits, I can just pull back. So it gives me a contravariant functor. Now I want to do two modifications to this functor. So one, I want to compose it with my core, right? So I haven't told you, but the core is actually a functor. And so I want to post-compose it with core to go from an infinity one category to a space. And also then I restrict to the full subspace of the core where elements are in a chosen class of maps S. So I don't have many diagrams, so at least I decided to like actually pictorially represent this, to have at least one picture in the whole talk. And so the way we should imagine this space, C over CS core, has like following shape. So a point is exactly is an arrow in S, which ends at C. Path is as well as an equivalence between two of these arrows and so on. So we should kind of think of the blue part as being like the topology part, and this red part is kind of just remembering that my maps all end up in C and all in S. So it's this is this space broken down as a, oh, it's already here. I forgot the S here, typo. Okay, so this is a space. Notice now I have defined a contravariant functor from C up to spaces. And so now I can repeat my almost the same question and ask for the presentability of this functor. And we say that an object is a universe if it exactly represents this functor I just defined. So let's see an example. An example of is in spaces is taking the category of kappa small spaces and then taking the core of that. Yes, I will actually say a little bit more about this later. So in 2 slides. But yeah, so this equivalence holds. I will explain a little bit more why this holds in 2 slides. Notice because we have whenever we have like a representing object, it comes with a universal fibration. So any object, any universe U has a universal fibration with classifying object. And in our example, the universal fibration is spaces stars. So what is that? That's just a category of pointed spaces. And the universal fibration is exactly the map that takes a pointed space and forgets the base point. So now we can actually see by example how we can recover an object.
So Nima, sorry, before you go on, it seems like you're, just to make sure I caught all the details correctly, you have 2 different notions of representability that you're using to define the subobject classifier and the universe. So the subobject classifier represented a functor valued in sets. So then by representability, you have an equivalence between the subobject functor and I guess pi naught of the mapping space. So
no. Omega, this is a literal equivalence of spaces. Omega is 0 truncated. I mean, here's the other way to think about it. Okay. A set includes into spaces.
Okay, thank you.
So this is a functor valued in spaces.
Okay.
Well, because every set is a space, and now I'm making this representability condition, and one particular implication of this representative condition, because it turns out to be valid in sets, omega will be a 0 truncated object always. So that's kind of follows from this condition.
Great. Okay. So that's great. Okay. Thank you.
But yeah, but it is not true notions of representability. Okay. All right. Here. So let's just see an example. As we pointed out, a point in the core space exactly corresponds to an object in the category. So if I take a point here, I can think of it as a choice of object, which we call X. So I call this up F sub X, meaning, well, I'm picking the point X. What is the pullback along the universal fibration? Well, what am I picking here in this the space above? I'm picking pointed spaces where the space itself is X. So in other words, I'm picking the space X and a base point in it. So this. The pullback exactly is a choice of point in X, but that is exactly equivalent to X itself. So the pullback of this vibration, the fiber of this vibration over the point is exactly the space that represents this map. Which is exactly what we expected, right? So I'm claiming that I can recover kappa small, like maps with kappa small fiber. In particular, I can recover kappa small objects because, well, the fiber over the point is itself. And so that's exactly what I'm doing here. All right, so now I have defined universes and I've defined a subobject classifier, so I can actually give a real definition for what elementary high topos is. It has to satisfy following 4 conditions. It has finite limits and colimits. It has a subobject classifier, omega. It is locally condition closed, meaning it has internal mapping objects. And there's a chain of universes, so that every map can be classified by some universe. And the need for this chain kind of can be very well seen exactly in this example for spaces. So I cannot have a space of all spaces. I cannot need to have a chain of various spaces of different size. And so when I want to abstract that definition, I kind of need to account for that and have a chain of universes, each of which kind of classifies a bigger universe. One thing I should say here, so this is not the only way of phrasing these conditions. There are different ways of removing some different conditions and like phrasing them in other terms. This is just a choice of one. You might see other ways of phrasing this that will probably turn out to be equivalent. Like there are a lot of like ways of phrasing this, and then all the equivalent as far as I know.
Nima, before we go on,
yes.
The set of maps we're classifying are the kappa small maps.
Here, yes.
I was wondering if you could just explain what a kappa small map is. It has What does it mean?
Here.
What does that mean? The points are kappa small, or every? I guess I think of kappa as being a cardinal, so it's something concerning a set, but the fiber is a concomplex.
Well, I haven't defined what kappa small space is. So here for this talk, kappa small space means a space for which all the homotopy groups are size smaller than kappa. And then a kappa small map is a map where if I take the fiber over each point, it has a kappa small space as a fiber.
Do you mean if you zero truncate it, it will be a kappa small set?
In particular, yes. Okay, so this is the definition that we will go for. Now my goal is to move on. Oh, let me give you an example before I do anything else. So we have already shown that spaces are an elementary topos, right? I constructed universes, I constructed a subobject classifier, and well, spaces have finite limits and co-limits, so that's not very controversial. So yeah, spaces is definitely an example. In fact, we can generalize this. So every higher topos, whereby higher topos now in the sense of Lurie, in the sense of the book higher topos theory, is an elementary higher topos. And here you have to kind of use fancy results proven in the book. So it's a combination of these two kind of main results. The first one says that this functor that I've described here, which now I have to like, so here I should point out, the kappa means kappa small objects in an element in a higher topos, which has a definition, but it's a little bit different. It's more general from what I said, but there's a definition of a kappa small object in a higher topos. And so the analogous functor for an arbitrary higher topos X takes co-limits to limits. So that is normally called descent. And then, well, every higher topos is presentable. That's kind of part of the conditions. And so presentability then implies that this functor has to be represented by some universe.
Can I ask a question? Can you hear me?
Yes, I can hear you.
Okay. I got here a little bit late, so maybe you said this before, but when you said a chain of universes, what do you mean by a chain?
Yeah, I was trying to like be a little bit vague here, actually. I mean, if you, I was thinking, in my mind, it's a poset, but what do you mean? Yeah, I mean, a chain. So a choice of universes. I mean, it doesn't, okay, so you mean it doesn't have to be linearly ordered? Is that the point, or?
Well, first of all, does it have to be linear ordered? Usually the word chain means a linear order, but
yeah, no, I agree. Yeah.
Also, does it have to be countable? Does it have to be a set size? Like the letter N sometimes represents a natural number. So do you mean a natural that's ordered by the natural numbers, or all ordinal numbers, or?
No, I don't think I want to make those comments. Yeah, no, I was actually trying to be a little bit vague here. So in my mind, there's a poset of universes.
Is it a poset or a class?
Sorry?
Is it a poset or a po-class?
Po-class. A po-class of universes, and every map is classified by some map in that class of this po-class.
Thanks.
Like I don't want to necessarily impose as like more conditions. But I was trying to like not precisely state that, but yes, that is how I would define it. Yeah.
So maybe to make the question more precise, do you mean the same thing that Mike means when he put forth the definition?
Well, I mean, almost. So like I said, like I didn't state all the details here, but so if I remember correctly in Mike's definition, then you have to also, for example, assume that all like the universe, what is classified, for example, is definitely locally condition closed. So every universe itself is locally condition closed itself. So there are like some subtle conditions that you can add to universe, like assume or not assume. And if I remember correctly, he does assume that every universe, like the subcategory of objects classified by a certain universe, is definitely locally condition closed.
Yeah, I assume that, and also that it's closed under co-limits.
And no, of course, and it goes under finite co-limits and limits. Yeah. So. And that's also what I'm assuming as well. Like I said, like I didn't want to give all details to like clutter the page, but yes. So normally when you want to do stuff, you would assume these kind of things about your universe to be able to.
So you are assuming that the universes are closed under.
Well, I am definitely assuming it's closed under limits and co-limits. I don't know about the condition closed. I feel depending on the situation. So.
Okay. Because to get that, you generally have to have the cardinal be inaccessible.
Yeah, exactly. If you actually want to, if you want to model it in spaces, then your cardinal choose has to be like inaccessible. Correct. Any other questions? Okay, then. So, so just to finish up the example, so combining this descent condition that this functor preserves, like takes full limits to limits, and the presentability condition for any presentable infinity one category, we get that this functor has to be representable, which gives us the universe we design. So for the rest of the talk, I want to kind of move on and see how we can do a bunch of like standard algebraic topological concepts in this context of this infinity one category. So for henceforth, I will only work in context of some elementary high topos. So step number one, natural number objects. So a natural number object is an object N and two morphisms O and S, such that for any other such kind of morphism, any other such diagram, N is the initial one. So N is the initial like choice of object along with one endomorphism and one morphism from the initial object that exists.
Can I ask quickly?
Sorry?
You said before that when you have a higher topos, you can always get an elementary topos from it, like the usual kind. I guess truncating it somehow.
So sorry, can you repeat that?
So you said with a higher topos, you want to get it. You want it to generalize the usual notion of topos. So if you
in my first slide.
Yeah.
So the statement is that if you take an elementary high topos and you take the subcategory of zero truncated objects, then that is an elementary topos. Is that what you had? Is that the question?
Yeah.
Or? Okay. So yeah. So I thought it was about that. Okay. So yeah. So that's actually relevant to the natural number object discussion. Yes. So yeah, the natural number object is interesting because it gives us an elementary way to tackle infinite questions. So let me give you one example. And here I'm like explicitly in a one setting. This is not an infinity setting. So this is like the exceptional one setting. If E is like an elementary one topos with natural number object, so you can kind of phrase this with just saying uniqueness instead of contractibility, then I can use it to construct certain free infinite algebras. So free monoids or free groups of any object without assuming that I have infinite colimits. So our initial motivation, like our initial intuition would be that if I wanted to find a free monoid on like an object, I would take the kind of like free infinite colimit of its products or something. But it turns out if you have a natural number object, you can kind of do like a similar construction without ever making a reference to infinite colimits. So that's like the beauty of having a natural number object. The thing is, in the classical setting of an elementary topos, we have to assume that a natural number object exists. So there are definitely like logical constructions where like, we don't have a natural number object. So like the easiest example is the category of finite sets, which satisfies all the conditions of classical logic. So like, no, sorry, all the conditions of an elementary topos, but doesn't have a natural number object. The change here is that when we move to this more higher categorical setting, we actually always have a natural number object. And okay, perfect. So given that I have a lot of time, I can actually tell you about the proof. That's nice.
The natural number object, if you know the process from going back to a normal elementary topos, does it break the natural number object? Is it? How do they?
Well, let me tell the proof, and then it should answer your question. If it doesn't, then I can discuss. All right. So how can we prove this? So the question that we want to ask is how can we kind of prove that this result holds? And the kind of the key insight is that we want to build some kind of object with infinite behavior, but out of finite objects. So how can we do that? And if I had like a live audience, I would actually like pause and look into people's eyes and make one of them answer. But you are too far away, so I'm like, I can't do that. the result is actually something that everybody has seen in like elementary algebraic topology class. So the background idea is the fact that pi 1 plus S1 is Z, which, well, everybody has seen, and like if you have taken, I don't know, an initial algebraic topology course. So this actually seems like a very, very kind of old school result, but if you think about it, it's interesting, right? Because S1 is a finite complex. Like I can build it out of a finite colimit. And okay, I say pi 1 here, but you can also replace this by the loop space, right? So S1 is 1 truncated, and so actually the loop space of S1 is Z. And the loop space is also a finite construction. It's a simple pullback. So it turns out that if I start with like this, I do this kind of simple construction, I get this object Z, which definitely has an infinite behavior. So we want to kind of reproduce that, but in an elementary high topos. Okay, so we do exactly what we do in spaces. So if I take the final object 1, I take the co-equalizer along and like a circle in a certain sense. So then we can take the loop space, or, well, the loop object in E, and the loop object would look something like this. So I can just call it omega S1. And then you can show that omega S1 actually does come with an automorphism S, and you can choose a map O from 1 to it. Okay, so up to here, then I have kind of like a choice of object which has these true properties. And now it turns out you can also show, I didn't write this, but omega S1 is actually 0 truncated. So that's also part of the thing you can prove. And now after you show that omega S1 is 0 truncated, you can actually study it inside the subcategory of 0 truncated objects, which is an elementary topos. And so in the elementary topos, you can then easily show it's a natural number object. Then you can actually construct a natural number out of it, that using like results there. But that obviously doesn't imply it's a natural number object in the original category. It just implies that it's a natural number object in this elementary topos. And here there's some like tricks you can use to translate it from the classical setting to the high categorical setting. And here I have used ideas from Schulman, who shows this in the context of homotopy type theory. And so here's like a good example of how homotopy type theory kind of comes in to help like understand concepts here. To summarize the proof, if you remember at the beginning of the talk, I talked about how we should think of an elementary high topos as being like this thing between spaces, homotopy type theory, and an elementary topos. All of these three concepts showed up in this proof, right? So I used my knowledge of spaces to first have the intuition that I want to study the loop space of the circle. Then I used my knowledge of elementary toposes, where natural number objects have been studied extensively, to actually build some natural number object in that subcategory. And then I use the knowledge of homotopy type theory to be able to kind of deduce some logical argument internal to like the infinity 1 category. So this is like a beautiful example where all these three kind of synthesize to give us the desired result. Yeah, so.
Can I ask a question?
Yes.
So go back a slide. So the automorphism little s there, can you say more about it? Sorry? Can you tell us what it is or how to define it?
Well, it's basically it follows from a descent argument. So there's one. Let's see. So the argument is that a map from any object into S1 is equivalent to a choice of object and an automorphism of that object. And how do we get those? So we get that object by pulling back along one, and we get, so the idea is that if I have a map here sitting over S1, I can pull it back to like a diagram, a co-equalizer diagram above it. So part of the topos theory condition is descent, and descent implies that if I pull back a diagram here, I will get like a co-equalizer diagram on top of it. So I don't know if I can draw it here now, but like you will get a co-equalizer diagram. Mm-hmm. And this particular implies that the map in between will be some automorphism. So like the automorphism kind of follows from this abstract argument of descent. Maybe there's a different argument, but okay. Yeah, that's the argument that I used.
And should I think of this as the +1 map?
It should be the +1. If you're in spaces, it is the +1 map.
Okay. I'm just asking because I know Robert Rose has thought about this, and he used, I think, the squaring map on the sort of power map.
But the squaring map is not an automorphism.
So it takes a loop and does squares the loop, right? So it's not. You're right. It's not an automorphism. It's an endomorphism. But that's fine.
For
successor map on the natural numbers is only an endomorphism. So anyway,
I see. To build natural number objects.
Yes,
that's
exactly.
the goal.
That's why
I see. Yes.
I was curious what you chose. Yeah.
So I see.
That's okay. Just a comment anyway.
Okay, that's interesting actually. Yeah, but no, this will definitely get you automorphism here in the context because like I'm using a descent argument here.
Okay.
Hi, sorry, another question. Sorry, we don't have a working camera. So you're saying that you're taking the smallest sub-object on the slide. We're wondering, how do you actually construct this, or is it not a constructive process?
Good question. So I'm using an argument in the elephant here. So I'm not that's the part where I'm not really a logician or type theorist, so I'm not sure if that is a constructive argument or not. But I can refer you to it if you.
Okay, thanks.
So I will not with it, but I can definitely refer you to like the specific result where like the theorem is basically that. So if you have an elementary topos and you have any such diagram, so an endomorphism plus a map from the final object, then you can construct the smallest subobject that is closed under the same maps.
So you can actually construct it.
Well, I mean,
okay, I guess.
Like I said, like I don't exactly know what constructive in this context mean, but like that is, yeah. So in the elementary topos, it seems, yeah, that's what the claim is.
I mean,
okay,
it's just the usual impredicative argument. You take the internal intersection of all the sub-objects containing it and that are closed under these operations.
Yes, that
using
is
the sub-object classifier.
Oh, I see.
Okay, yeah.
So
okay.
it's constructive in the sense that it doesn't use excluded middle, but it's impredicative.
Okay, thanks.
Yeah, exactly. So I don't exactly know if that means the constructive that you meant, but yeah, exactly. It's an intersection argument.
Yeah, no. So this, yeah. So this is a completely satisfactory answer. Thanks.
Oh, perfect. Okay.
Yeah.
Any other questions about the proof? Okay. So then now that we have an NNO, we can do stuff with it. So one thing I will need for the next section is a notion of like sequential colimit. So let me like say a little bit about this before I move on. For me now, and so this work is mostly based on, or completely based on like ideas of Rasekh in this paper, The Joint Construction, where he works in the context of homotopy type theory and kind of like adapted it to the setting of an elementary topos. Because what you really need is like a universe in a natural number object and like colimits. So I just define a sequence to be a map from a natural number object to the universe. And well, by a definition of the universe, this is equivalent to kind of like a choice of map over a natural number object, right? And so a sequential diagram then is, well, is a map between, well, one sequence and, well, itself. But here, so I wrote n+1. So this basically means I kind of shifted the fibers by one using the successor map. And I would normally depict it like this, right? So I depict it as kind of like a diagram, but in the category it would look like a map of these total objects.
This is a diagram in the category, right? It's not.
This is not actually a diagram. The diagram is just a map from this object to this object in the category. But like the way we think about it, like the way I would like be depicted as this diagram, but there's no actual infinite diagram in the category. If that helps. So this is just like to guide, but the actual category is I have this one object, and then I just take a map between this object and itself. But I think I'm kind of like shifting the fibers. And so now that I have this map,
sure. Sorry, I'm just confused because you're using hot notation. Is this in hot or is it?
No, this is inside E. I'm using hot notation because, well, that's the best notation to use in this context, in my opinion. But it's not in hot. This is inside E.
So this thing that you're writing as sigma n and n of an is not actually a sigma in any sense. That's just an atomic notation for an object.
Well, I mean, it would be, right?
But it
if
isn't.
we talked about hot, what is sigma? It's exactly the universal object over the end over the universe, right? So, but no, it's not. And like, I don't know. Well, here's a good way to say this. This object is the morphism that classifies the map AN. So it is a sigma in that sense. It is a total object that classifies exactly this map. Right, so sigma AN is the object over N classifying the map AN to the universe. In that sense, I'm thinking of it. So it works very well with this context, but it's not a sigma in the hot sense, I guess. But it would be like, if you want to implement hot in some sense, then this should be the sigma, right? Like this is total space.
So as Mike is saying, it's just sigma of AN is just some object. You know, there's no sigma.
It is one object. But well, it has exactly fiber AN, right? So notice N has the natural numbers. I can take the fiber over a point. The fiber would be exactly AN. Over the fiber over the integer N would be AN. Okay, so now that I have a map, I obviously also have the identity map because we're the same object. So I can take the co-equalizer. And the co-equalizer will exactly be what we call A infinity. So it plays the role of sequential colimit. All right, so notice then A infinity kind of behaves like the colimit of this diagram, but internal to the category is just defined as a co-equalizer. So it's a finite colimit, and so it's perfectly defined inside E. Like there's no actual infinite colimit happening.
Yes.
Sorry, I wasn't expecting those to be the same object. Can we go back one slide? I interpreted the codomain of the map Fn as the total space that's classified by your map into the universe precomposed with the successor map.
No, so yeah, that's what I'm saying. Like here I'm using notation. So these two are the same object, but they're distilling differently over N. So this AN is just P, but this one is SP. So there's a P and then there's S successor, but it's the same object.
I see. And so the co-equalizer diagram on the next slide is not over N.
This co-equalizer diagram is not over N because I don't want to respect the fiber. I want to actually map one object to the next one.
Okay, thanks.
Yeah. Yeah, so in other words, whenever I can define, so the upshot is whenever I can define any map like this, like a map like this, I can use it to kind of get like this A infinity. So that's the game. Okay, so I want to use this to build truncations. Okay, so good, 15 minutes should be enough. So next part, truncated objects. So truncated objects are a really, really big deal in algebraic topology because, well, they have a simpler structure. And so if we can look at truncated objects, we can very often better understand them. It helps us understand more complicated objects. So let's see, an object in a space is n truncated if, well, all the homotopy groups above a certain level are just trivial. And I can just say an object in an infinity 1 category is n truncated if the mapping space, and so here I'm using the fact that whenever I have to morph objects, I have a mapping space. If the mapping space is an n truncated space. The cool thing about truncation is that in spaces, there's a truncation functor. So there's like a universal way to take any space and truncate it to an n truncated space. Yeah, so how does the proof work? So the idea of the proof is that I can take my space, I look at it, I realize there are a bunch of higher dimensional holes I don't like. I take disks, I put them in, and I fill all the holes. Then I realize, wait, while filling them, I made more. So I have to fill in 2. And I keep doing this, like many times. And eventually they're all full. And so the output I get is perfectly truncated and nice. So this is kind of captured under the slogan of the small object argument. And this works very well However, there's no way this ever works in this setting because it's highly infinite. So our goal is to find an analogous finite argument. And so the goal is to we want to show that this result holds. That if I take I can build a functor tau n from an elementary high topos to its n truncated object. And here again, I will use a lot of the ideas by Algebraic in the context of homotype theory, who did this kind of same concept in the context of homotype theory in his paper, The Joint Construction. So how does the argument go? So roughly speaking, there are two steps. The first step is I can take an object and I can define this sequential diagram. So I just remind you, I'm depicting it as this sequential diagram, but really it should be thought of as a map between like the total spaces. I'm just depicting it this way because it's just way easier to understand it. And so the upshot is that the sequential colimit of this diagram is the -1 truncation of the object A. And here join is just defined well as the push out along this product projection. And so I should point out, so this is exactly the analog of theorem 3.3 of the paper, The Joint Construction, but the proofs are not exactly the same. So I took that result, but then I didn't exactly took the proof. So the pieces of the proof are the same, pieces are not. So it turns out some concepts in homotype theory are just easier to translate, and some are just like way more complicated than they should be. Because like each one of these two languages have to have their own kind of like weak spots and good spots. So it's not a direct translation of the proof, but it is to some extent. So we have a -1 truncation. How can we use that to build higher truncations? We just don't want to have n equals -1, the other integers. So how can we do that? Here's the idea, and that actually is true for spaces. So if I have a space X, and let's say I know how to n truncate it, and I want to n+1 truncate it. So I'm doing some kind of inductive argument. Then what I can do is I just take all the loop spaces at any point and n truncate the loop space. And that will n truncate, and that will n+1 truncate the space by n truncating the loop space. So how can I make this in a more actual argument? So so here's the diagram. I can take my space X and map it to this the collection of maps from X into the space core. And where do I map it? It takes any point to the path space. The space of paths into X. But then what I do is I just n truncate all of these. So these are exactly my path spaces, right? So these are the analogs to my loop spaces here. And so after I've taken the path space, I can just n truncate those. And then I just take the image of X inside this construction. And that will exactly be the n+1 truncation. It has it's exactly saying, take my points here, map them over, but then along the way, n truncate all the path spaces. In particular, n truncate all the loop spaces. And so, the resulting object will exactly be the n+1 truncation. So funny fact is, so for those, depending on whether you can see it or not, but essentially the first map here is actually inclusion. So the fact that this is an inclusion is basically a corollary of the unidad lemma, if you want to. So this is exactly kind of like a unidad lemma for spaces. So in some sense, what I'm doing is I'm just like enlarging X and then n truncating it inside this bigger kind of space. The beauty of this argument is that it generalizes perfectly, because spaces core was exactly what we thought of as the universe, and universes always exist. So what I can do is I can simply take exactly this diagram and just make it abstract. So I get this. I just take my X, I embed it in this U to the X, where what is this map? This map is just a map that classifies the diagonal. And then I n truncate all this, and then take the image. And notice the reason that I can take the image is exactly because I have -1 truncations, right? So a -1 truncation of a map is exactly taking factoring it into the surjection by inclusion. So I'm explicitly using the fact that I already have regular one truncations to make this inductive argument work. So there are more details, but that's like a rough argument. So this, as I said, this argument has been implemented by Algebraic in the context of homotopy type theory, and I kind of took that idea, and again, so some of the proofs are, like most of the proofs are different, but some of them are the same, and then you kind of can get the same result. So yeah, so there are some similarities and some differences. Any questions?
Can you explain why it's the diagonal map?
Well, the diagonal map, if you think in the context of spaces, the diagonal map, you should think of it as a path vibration, right? Like think of x as being x to the I, which is equivalent to x, right? Like there's a space they're equivalent. And then this will be like a source target map. And then the fiber over any point would exactly be the loop space. But inside an infinity one category, I don't need to do this, right? Like my diagonal map is the path vibration. Does that answer your question?
Kind of.
Okay. And we can also discuss this further, but like I'm trying to generalize, I kind of get this, right? Paths from something into X. And so if I think of this as being paths over like, well, paths in X that are sitting over whatever points, then that is exactly the analogous object. The thing that we have to like, the thing that's unfamiliar here is that in difference to like a model category, you don't need your like maps to be fibrations or whatever. So the diagonal is already the correct map. Like you don't have to like fibrally replace it by some kind of like path object. That's kind of like the difference that's happening here, right? So if that was a model category, I would have to take the diagonal, fibrally replace it, which in a particular case of spaces would be literally like the paths in X, but in like a model category would be like the path object, and that would give me the right result. Okay, so we're almost done. Now that we have truncated objects, and so we have connected maps, we can look at one of the like very classical results in algebraic topology, namely Blakers-Massey theorem. So the classical statement of the Blakers-Massey theorem is basically, well, very established. Just like this is a reminder, but it's basically saying that if I know that f and g are connected, then I can find a relation between the map from Z to this pullback. We want to say up this. We want to show that this also holds an elementary topos. In order to do that, I need three definitions. So first of all, a weak factorization system is a choice of functors so that I can like factor my map into the image of, well, those functors. And then we think of like L and R, well, the notation is chosen because we think of them as like right and left classes. So this is just a.
I think normally people would call that. I think normally people would call that a functorial factorization.
Okay. Where did I pick out the? Okay, I'm.
A left class is meant to go on the right.
Sorry.
A left class is meant to go on the right.
Left classes. No, I mean if you write them as like maps followed by each other, you would have the left class then followed by the right class. Like if you have two arrows and you draw them, F would factor as first the left map and then the right map.
Okay, if you draw the diagram, it makes more sense.
Yeah, I know it's confusing because composition is reversed. Like that's just the notation. Yeah, I don't know. I mean, notation. I don't know. Like, okay, so if a functorial factorization system definitely makes sense. I don't know. Like for some, I'm following the notation of the paper I will reference in 2 slides, and they call a factorization system this. So I'm just sticking with that notation. But yeah, I think that actually makes a lot of sense. So, but a factorization system here is defined as, so you have a weak factorization system, but you're also assuming that if F and G are in, there's a typo here. This should be a G. If F is in a left class and G is in a right class, then the space of lifts is contractible. Yeah. And so finally, a modality is any factorization system in which the left class is closed under base change. So yeah. So I can factor any map. The two maps have the property that they kind of like, there's a unique way to lift against them. And the left class is closed on the base change. And actually the right class is also closed on the base change, but that's always true. Okay, so now here's a really cool result that was proven by Anel, Biederman, Finster, and Joyal, is that if I have this push-out diagram such that this push-out product map is in the left class, then this map FG will be in the left class as well. And now you might say, okay, this looks like completely different from the theorem you just gave. But it turns out you can prove the very standard Blakers-Massey result using this by using the modality where L is the n-connected maps and R are the n-truncated maps. So here you obviously have to prove that it's a modality, but that's not too bad. And then the classical Blakers-Massey will just follow from this more general thing. So doubly fortunately, so here's what I did. I just looked at their paper because they proved it. Oh, I didn't. So they proved it for what I called here a presentable elementary higher topos. What they just called as a higher topos, because that's what a higher topos is. But in our context, so they kind of assume the presentability condition. But it turns out they never use it in an essential way. So you cannot remove, you're able to remove the presentability condition from the proof they present. Their proof primarily relies on a descent condition, and descent holds in an elementary and in a higher topos. So that generalized Blakers-Massey theorem, and in particular then the classical Blakers-Massey theorem, holds in an elementary higher topos, according to their proof, with minor modifications. So they're 3 or 4 lemmas that you have to adjust, but it holds in mostly the same way. So then why would we care about presentability? In this context, presentability would be interesting because it allows us to construct modalities. So one kind of, well, I don't know, one drawback of working in this elementary setting is that we're not able to construct modalities in an easy way we are in a presentable setting. So in order to build a modality, you have to very explicitly give a construction, the way I just gave you for the truncation and connected maps, for example. Whereas in a presentable setting, you can just make them appear, right, using presentability arguments. So as of now, I don't know if there's any other modality other than n-truncated and connected maps that exist by default in the topos. But obviously, then you can also assume their existence, right? So if you want to do more differential stuff or more topological stuff inside a topos, presumably you can add some modalities, and then Blakers-Massey would hold for those as well. Okay, perfect. I have 2 minutes. So last time, where can we go from here? So there's lots of places to go for an elementary topos. These are specifically for algebraic topology. So where can we take the algebraic topology of this topos? Well, one thing is we have proven that there are truncations, and well, they're always spheres, because that's easy. And so we can talk about homotopy of spheres. So what are the homotopy of spheres, and how do they compare to the classical homotopy groups of a space? Right. So another question is, now that we have Blakers-Massey, so one very, very kind of valuable corollary of Blakers-Massey theorem is the Freudenthal suspension theorem, right, which kind of gives us this argument that the homotopy groups stabilize. And so in particular, we can also so elementary higher topos have finite limits, so we can talk about their stabilization. And so in the light of these results, then we can now ask for the comparison between the stabilization of elementary high topos and, well, the stabilization of spaces, which is spectra. And now another thing is that we can wonder now is now that we can kind of truncate our space, so I can take an object, I can find its various n truncations, and now I can ask myself, can I build a Postnikov tower? And well, you can, but can I use it to do stuff? Can I use it to reconstruct my object? Can I use this tower in some effective way, the same way we use in spaces? And so one question that kind of comes up there is do we have Eilenberg McLean objects? So objects that only have non-trivial homotopy information at certain truncation level. Because that's kind of the thing that pops up when you look at Postnikov towers. So these are 3 possible places you can go from here if you only focus on the algebraic topological aspects of the topos. Okay, and with that, I end my talk.
Okay, I guess I was muted, but you all knew what to do.
Yeah.
So I'll mute everyone again and unmute Nima, and then we will ask if anyone has any questions. Or comments.
I may as well ask a question.
Yep, go ahead.
Do you have any examples of elementary higher toposes that are not presentable?
The eternal question. The answer is no, but I'm thinking about it. And the place to look for is so like the thing. Like at first, I thought a lot about like maybe building some kind of spaces with some finiteness condition, but they all fail. Turns out elementary like topos, when you go in a space direction, they're all like vastly infinite. The place that I'm looking at right now is so there's this paper by Kapulkin, Lumsden, and Blavatsky, where they basically show that, well, Kahn complexes are basically what they show is that Kahn complexes have an elementary topos, right? They construct universes assuming that you have weakly inaccessible cardinals. The hope is that you could do that in an elementary, that same argument roughly, or something along the side, how in an elementary topos with some universe assumption. So a realizability topos, in which you assume that it has sufficiently many universes. So that's also a problem. Like, so one problem that comes up here is that we know that the zero truncation of every elementary topos is an elementary topos. So presumably, that's you have to guarantee that if you zero truncate, you get elementary topos. And the way I see things is if you zero truncate the universes, presumably they should give you universes of elementary topos sense. So there's like this notion of a universe in elementary topos, which is, well, a little bit different. And it seems that, so I've tried to look into this, and it seems they're not that, like, we don't know of many elementary toposes which have universes, like other than realizability toposes. So there's like this obstruction there right now. You can't just pick your favorite elementary topos and try to like build elementary topos out of it. You have to like start with one that has the right conditions. But yeah, so the idea is to start with a realizability topos with some universes and try to see if you can kind of build like Kahn objects in there or something. So that's kind of the hope. But it's not done in any sense.
Do you have any examples of an elementary topos that is not a higher topos? In the sense of...
Didn't I just answer that? Or sorry?
No, as in an example where it's not a, pre-sheaf topos, higher pre-sheaf topos, I think.
Yeah, that's exactly what that is exactly the thing, right? So an elementary higher topos that's not presentable.
But I don't know,
right?
Can there be presentable ones that are elementary but not? I don't know.
So every higher topos is automatically presentable. That's part of the definition. But it also satisfies.
Right, are there presentable elementary topos that are not higher toposes?
No, that's not possible. If you are the second if and only if kind of thing. So if a presentable an elementary topos, elementary higher topos satisfies descent, and every presentable topos that satisfies descent is a higher topos. Every presentable infinity one category that satisfies descent is a higher topos.
So you're saying if it's presentable, then that's equivalent to it being a higher topos?
If it's an elementary higher topos, yes. So like if you take an elementary higher topos, then being presentable and being higher is equivalent because you already have descent.
Okay.
In the one topos case, people use the word Grothendieck to indicate the elementary toposes that are sheaves. So you could use that here too.
Yeah, I like that. Grothendieck higher topos should be like, the problem is like the name of the book is higher topos theory, and so somehow there's that kind of stuck. Like I agree that we should change that. Like we should be like Grothendieck higher topos and elementary higher topos to like distinguish between them.
So continuing the same theme, do you think the initial model of type theory of Hott should be an elementary infinity topos, but not a Grothendieck infinity topos?
That is not really like kind of my that's not really like, I don't know. The question is where would a presentability come from like this axiomatic framework? So
where would what come from? Sorry.
Yeah, I mean you need a like if it's Grothendieck, then it would be presentable. And I don't know, like is it like something like, is there a way to like create small generation or like something like a presentable condition?
Yeah, no, I wouldn't expect it to be presentable.
Exactly. So I also would be like, I'm not really an expert in type theory per se.
Yeah.
But my understanding from the framework I've seen is I don't see how you would create like a small set of generators.
Mm-hmm.
out of like this axiomatic framework. So yeah, my assumption is if that was like a topos, then it would be elementary, but probably not perpendicular. But I'm not sure. That's not something.
Definitely won't have all co-limits. So
Speak up, Chris.
it won't have all co-limits. So
Right.
definitely not presentable. And Louis has a question.
Yes.
More of an observation. So
You got to speak up. We can't hear you very well.
Maybe there's yeah. So you were saying that you're not aware of other modalities or factorization systems other than n-connected and n-truncated. I believe that you can construct using sequential colimits. You should be able to localize with respect to any map between compact objects. For example, a map between the one sphere and the one sphere. I think Egbert was also thinking about that. I think he proved it on paper. So, for example, you could construct localization at primes or stuff like that.
Yeah, I think there was recently like this paper on the archive, right, of like this group of people, Egbert, you, and a couple other people, presumably from the MRC or something.
Right.
That did some localizations in HOT or something. Is that what you're referring to?
Well, there we use a higher inductive type, but what I'm saying is that you can get away with a sequential colimit. So really, you don't need any weird colimit. With finite colimits, you should be able to do that.
I see. Yeah, I mean, yeah, that's I see. Yeah, that makes sense. I mean, this is roughly like a similar argument, but okay, I see. Yeah, that would make sense. I'm not familiar with the work. I could believe it. Like it sounds reasonable to me that this should be like something like that.
Right, but we don't expect that to be a modality, just a reflective subcategory, right? So I don't think it'll quite give an example of another modality in general, but it's almost a modality.
But you could analogously nullify at any compact type and get a modality.
Yeah, there you go. Yeah, so you could do that. You could nullify the circle, for example. Yeah.
Which gives you the zero truncation if you nullify the circle.
Oh, that's true. We already knew that one. Yeah.
There are also a few other modalities that you can construct directly, like in HOT, presumably in a topos too, like an open modality and a closed modality, and a double negation, just using the structure.
Yeah, I see. Like double negation. Yes, I don't know exactly open and closed modality. They are presumably topological, or is that I don't know, but like double negation sounds right. Yeah.
So, sorry, when I've heard you talk about elementary higher toposes in the past, and you were talking, one of the axioms involved a complete Siegel universe. I'm wondering if you could explain sort of how that structure is repackaged in the definition, maybe in this chain of.
Yeah, well, I didn't do it. So I tried to not use it because it's harder to explain to like people who would just want to listen to a talk, but so let's see. Well, it went too far. So I have like this universe, right? So this like universe should play the role of so like a universe should play the role of some kind of like the zero level of a certain like internal infinity one category, internal to that category. And so like what I would need then in order to actually make it, like I would need like some kind of higher like the mappings, like so the easiest way for me to construct like an internal infinity one category is just by building an internal complete Siegel object, right? Like a sequential diagram in it that satisfies well the Siegel condition, the completeness condition. And so then you have already this, well, this zero object. What I need is the one object, and the one object it consists of. I should think of it as the thing that fiber over the point is mapped from this classifying object to another one, right? So how does that make sense? The fiber over a point X here is exactly the space X. A fiber over the point Y is exactly the space Y. And what should my mapping object be? Exactly maps from X to Y. So how can I actually build this? Well, I do the standard homotopy type theory trick. So I pull back, I pull back U along U times U. So I pull back along the pi1 and pi2 projections, and then I take the internal mapping object of like U star times U to U times U star. I don't know, like I don't have anything to write on, so maybe it's not that helpful, but you can actually like build this this mapping object that I need, like the one object of my complete single object, using like locally Cartesian closed condition. So I use this here. So I use this local Cartesian closed condition, can drop it, but then strengthen the universe condition, like make it some kind of like simplicial object. I don't know. Does that answer your question?
Not really, but so is this chain of universes a simplicial object?
No. The chain of universes is like a chain, but then I can make each one step a simplicial object. And then it would be like, I could make it a chain of simplicial objects.
Okay. So somehow for each of the universe. So I guess I'm thinking of UN as the N is indexing some sort of size, maybe.
Yeah, no, in hindsight, I tried to make it the N to like make it look less threatening, but in hindsight, I realized the N was not a good choice. It seems to have more confused people, but I was like trying to have like a bunch of objects that like one bigger than the next, and then like, you get like, but yeah, there should be like some kind of co-class as well, as we agreed on, like a class of objects which are like, partially ordered, and every object is classified by one of the universes. And I can extend in universe to like a simplicial object.
Okay, thanks.
Yeah.
So you said every elementary one topos is a higher topos, right?
No, that's not true.
No, okay.
Topos theory is not like, this is like subtle. Like one category is an infinity one category, but one topos is not itself by default like an infinity topos. And so what is true is that a Grothendieck one topos, so a sheaf in sets can be made, like you can like, there's a way to make it into a Grothendieck infinity one topos. But not by embedding, like if there's no like embedding, like it's not itself, you can like modify it to one. But it turns out,
I had the example of finite sets in mind, and I was wondering when it became an infinity one topos, where its natural number object came from.
No, exactly. I wasn't finished. Finite sets is not a Grothendieck one topos.
Exactly.
For the elementary case, that is not true. You cannot take every elementary one topos and make it an elementary infinity one topos. You can take every Grothendieck one topos and make it into an Grothendieck infinity one topos.
So when you're saying that they generalize elementary one topos, it's not strictly true.
Yeah, definitely not. No, yeah, that is not so. Like the initial thing is more like the best way to think about it is really like a triangulation, right? So it's vaguely in the neighborhood of these 3 points. So I give you like 3 points in the map of math, and I say wherever elementary topos is, it has to be close to all of these. But it's not actually any of these spots. So there has differences with like all of them in some sense, but also similarities with all of them. So like so there are differences. So the question then obviously becomes which elementary one topos we can extend to an elementary infinity one topos. So that's exactly something that I'm thinking about. I don't know. It's still a little bit subtle, but yeah, you need conditions. So you need like your elementary topos needs to have a natural number object, for example, right? Because, well, I just showed that the infinity topos will have a natural number object. But there are also other conditions that I probably have to.
Sorry, can I suggest a conjecture maybe that addresses this question? Which elementary toposes arise as zero truncations of elementary infinity toposes? So if we take this point of view of the conjecture that elementary infinity toposes are exactly models of Hot, and then zero truncation corresponds to taking the extensional type theory. So you should probably, so my conjecture, which is like made up right now, is that these will be the toposes that arise as models for extensional type theory with prop of sorts and inductive types, essentially. So that's just a conjecture based on 30 seconds of thinking, so likely true.
Yeah, I mean, I don't know. I have nothing. That sounds reasonable, but I don't know.
I don't understand why you want to call it an elementary higher topos if you don't, because the reason they called it an elementary topos is because they kind of generalize the Grothendieck case, right? As much as possible. But how sure are you this can't be generalized further?
I mean, how sure can I be that a definition cannot be generalized to a further definition? I mean, I can't.
But no, because I'm trying to understand why this deserves to be called an elementary higher topos.
Yeah, that's a good question. I don't know. I mean, I would not go as far as declare that this is the one definition, and if anybody says otherwise, they shall be executed. I think this is a very, very young field, and there's a couple of people kind of thinking about this, and maybe that is exactly the perfect definition. Maybe 10 years from now, we look back and realize, oh, we should have tweaked maybe condition in this condition a little bit, or maybe we find like something more, like as you pointed out, like some general condition that applies this, but still has the power to deduce the things we want it to. Like, I would not go as far as declare this to be the answer to everything. I mean, there are some like reasons, like if you work with them, you actually see, okay, this kind of like works well. I mean, like one of the guiding, which already like Chris pointed out, like one of the guiding ideas is that it should correspond to models of hot. Right. So if we eventually figure out that no, models of hot are like elementary topos, anti-topos minus or plus one or two conditions, then maybe that's the more reasonable condition. But if you actually can prove that these are the models of hot, then I think that's the excellent definition. Right? That works well. But I agree that this is not like settled math. It's like very new and very developing.
More comments, questions, conjectures?
Yeah, conjectures are good if you have any more conjectures.
May I have a naive question? Can you hear me?
Yep. Go ahead.
Yes.
So you mentioned 3 applications of this elementary higher topos theory to algebraic topology. Are they totally separated applications, or they have some interactions and interplays between each other, like the 3?
Sorry, can you repeat? Like, are the applications in the? Sorry, can you repeat the
last
last part?
slide.
Sorry.
He meant
In the last part, you mentioned 3 applications to algebraic topology of elementary higher topos. So are the 3 applications are totally separated to each other, or there are some relationships between each other?
Do you mean like, so these 3, like natural number logic, truncation, and Blakers-Massey, or do you mean the last slide?
Yes.
So, wait, which one? Right.
I mean, these 3 applications, are there any, relationships between each other, or they are just separated applications?
Well, I mean, each one builds on the next, right? Like on the previous one, right? Like, so I start with natural number objects, and I use it to define like sequential colimits. Then I use sequential colimits to define -1 truncations, and then I use -1 truncations to define n truncations. And then I use truncations and connection. I use this actual construction to show that the modality. And then you use Blakers-Massey to show that you have the classical Blakers-Massey in infinity 1 topos. So like each,
that's the logical flow. Yeah.
Like each kind of construction needs the previous one to get the result I want.
Okay, that makes it clear. Thank you.
Okay. Yeah.
Anybody else?
I definitely don't want to be executed, but just to say that, so elementary topos, like the idea of that is not, we're defining it in elementary terms by listing the properties that the category has, rather than saying it's a category of sheaves. That's where the name comes from. And so in that sense, that's a perfectly fine definition of an elementary infinite topos. So just wanted to say that even if it may be generalized, I don't think that's a relevant discussion. I think this is a perfectly fine definition, and yeah, it's a very good definition to compare to Hall, assuming we can agree on what a chain is, but that's a separate discussion. So yeah, please don't execute me.
But it seems to me like it's more an elementary higher topos with a natural numbers object.
Probably natural numbers object and a lot of stuff, a lot of other stuff. But that's not the problem. That's not the problem at all, because I think if anything, it rather points to the fact that the definition of an elementary one topos is wrong.
I mean, maybe it's not about right or wrong. I mean, there are differences in the structure. So here's maybe an easy example to keep in mind, right? So the -1 truncation here is like this infinite chain, but you can there's like obviously like similar result in the role of elementary topos theory, right? Like there you just call it epimonofactorization because you don't need to like fancy truncation language, which we are just working in one categories. But so you can look at any proof of like the epimonofactorization, and that just like you take equalizers and you do some stuff and you're done. That proof doesn't generalize because, well, you have homotopy theory, because your equalizer would be like a homotopy equalizer. You actually need like an infinite tower to get the same result. So yeah, so for example, if you worked in an elementary topos without natural number object, you have an epimonofactorization. But if you try to do that same thing, as far as I can see, I don't see any way, any finite way to get like an epimonofactorization in an elementary higher topos, like whatever your definition would be. So there's something more complicated about these like higher, like basically spaces and like homotopical structures that kind of demand the existence of certain kind of structures like this. I don't know. So yeah, I see your point. Like your point is that you have a natural number object in one and you don't have to assume it, but there are also like different demands that you're trying to axiomatize something else. So actually, from my perspective, there's a reason why it should be an elementary higher topos and not a higher elementary topos. Like I'm not trying to generalize an elementary topos to a high categorical thing. I'm trying to generalize a higher topos to something elementary. And these two don't have to be the same thing. So your aim is kind of maybe like your perspective is more to like make an elementary topos higher. But
yeah, I think that's what was confusing.
That might be something different. Sorry?
You got it right when you said when you swap higher and elementary round, it makes more sense.
Yeah, I think I think the perspective is different. Right? I think they don't commute. Right? This is a non-commutative word or something. Yeah. So from at least from my perspective, and I think from the perspective of some of the people working on this, it should be really the elementary analog of the higher topos, and so you're trying to get those kind of results in this elementary setting. And that might differ the same way set theory differs from spaces. We don't expect all the results to be the same in them, and so there should be analogous differences between elementary higher topos and elementary one topos. But like I said, like I'm not like dogmatic about this. Like if there's different definition that gives us the right results, then well, that's good. Like I would be happy with that.
Okay, last call for questions.
Okay, sorry, I'll just maybe say one other thing about that. So the point is that in elementary topos, we can interpret higher order into intrinsic logic, whereas we want to interpret, univalent type theory in the higher topos. So the truncation of that is exactly extensional type theory and not higher order logic. So the mismatch between the two is exactly, I think, what you see as the mismatch between zero truncated objects in an elementary infinite topos and an elementary one topos. So I think the comparison between logical systems perfectly would explain the mismatch between the two notions on the categorical side.
Is that really true? I mean, you can interpret extensional type theory in an elementary one topos as usually defined. Is it the universes you're talking about?
No, inductive types, for instance.
Well, there are no inductive types in Nima's definition here either.
No, but like you get, for instance, the natural number object, right?
But Nima didn't put in a natural numbers object either. It's not part of the definition. It follows from the definition.
Right. But so I'm assuming that natural number object is not the only thing that follows from this definition.
Well, yeah.
So I would imagine that there will be something, that there will be certain class of inductive type that you can get out of this definition. And I think that exactly is the class that would explain the difference. That would be the class that I would not see in the higher order logic.
I would tend to put the blame on the universes instead of on the inductive types that you can construct from them.
So
I mean, isn't it the universes that are the real difference?
Well, the universes are also the difference between higher order logic and EDT.
Right. That's my point. That's the universes and not the inductive types.
Right. Okay, but that's also my point.
Okay.
Well, my point is that it's both, but yeah.
Okay, anything else? All right, well, let's thank Nima again. Oh, sorry, I did it wrong. Okay, so thanks again, Nima, and our next talk will be in 2 weeks. We're starting with our every 2 week schedule starting this week. It'll be Zeeman Huber in 2 weeks, and I hope to see you all then.